An 87 kilogram person stands on a scale in an elevator. Find the force that the scale exerts on the person, and therefore the force that the person exerts on the scale, when the elevator A stands still, B moves downward at a constant velocity of 2 meters per second, and C accelerates downwards with an acceleration of 1.3 meters per second. To begin solving this problem, I've copied the force diagrams from the previous slide, since this is the same scenario. Since part A asks when the elevator is standing still, I'm going to reference the first set of force diagrams. Whenever we solve problems involving Newton's second law, it's important to first draw an interaction diagram, then a force diagram, and then take that force diagram and write out the sum of forces in the y direction. We'll then use Newton's second law to set the sum equal to the mass times the acceleration of that object. Let's write out the sum of all of the forces acting in the y direction on the person in this scenario. If we define up to be our positive direction, I'll subtract the force of the earth on the person, or the force of gravity on the person, from the force of the scale on the person, which pushes upwards. And by Newton's second law, I know that this sum of forces will be equal to the mass of the person times their acceleration. But if the elevator is standing still, then they are not accelerating. So I know this will be 0. So I know that the sum of all forces should equal 0. So if I were to take my sum of forces then and set this equal to 0, I could solve for the force of the scale on the person. So I've gone ahead and expanded the sum of forces, and I've written that as F of scale on person, FSP for short, minus F of earth on person, FEP, equals 0. Therefore, I know that the force that the scale exerts on the person must be equal to the force that the earth exerts on the person. And I know that from earlier, this is equal to the mass of the person times g, right? This is our weight force. The force that the earth exerts on any object can be found by taking the mass of that object and multiplying it by g, which in this case will be 9.8 meters per second squared. And I want to point out that we're going to use g as a positive from now on when we solve problems involving forces. And that's because we're accounting for the negative sign when we subtract the forces. So we don't need to worry about making g negative. When we're solving problems involving net force, we're going to account for that negative sign somewhere else. So in this case, the force that the scale exerts on the person would be equal to the mass of the person, which was 87 kilograms, times 9.8 meters per second squared. And since I'm using kilograms, meters, and seconds, I know I'll get a Newton when I'm done, and that'll give me a Newton of 853 newtons, rounding to the nearest Newton. All right, now for B, we're told that the elevator is moving downward at a constant velocity. All right, now I want you to think, if the elevator is traveling at a constant velocity, what is the acceleration of both the elevator and the person? If you said 0, you'd be right. Constant velocity means that the velocity is not changing. Therefore, we cannot have an acceleration, which we know as a change in our velocity. So this means that A is going to be 0. So the forces are the same as when the elevator was standing still. Because there is no net force, right? There is no acceleration. The force upward, the scale on the person, must still be balanced with the force of the earth on the person. So I know then that the value won't change. It'll be the same as it was in part A. Because, again, my acceleration is 0, both when I'm traveling at a constant velocity and when I'm not moving at all. How about if the elevator is accelerating downwards with an acceleration of 1.3 meters per second squared? I added the square there, my unit was a bit off. So in this case, I do have a net force because I am accelerating downwards. So let's write out the sum of forces in the y direction again. Notice it's going to look the exact same because I have the same two forces acting on the person. So it's still the upward force that the scale exerts on the person minus the force that the earth exerts on the person. Now this time, that's equal to MAY, just as before, but A is not 0. A is actually going to be negative 1.3 meters per second squared. Why negative, you ask? Well, if I'm accelerating downwards and I'm calling down negative, then my A would be negative here. To isolate the force that the scale exerts on the person, which is what I want, I'll add the other force to the other side of the equation, and that will give me MAY plus FEP is equal to that scale force, which would be the mass of the person, 87, times negative 1.3 meters per second squared. This is in kilograms here. Plus the weight force of the person. So that would be their mass, again, times 9.8. Again, making sure that we use a positive 9.8 here. And I'll get an answer here of 736 newtons. That is the force that the scale exerts on the person. And therefore, that's also the force that the person exerts on the scale. This is what the scale is going to record. And notice, right, this value is less than 853 newtons, which is the actual weight of the person, right? So the scale is going to feel like the person's weight is smaller. Even though the person's weight hasn't actually changed, the scale is going to feel a smaller pushing force from the person, and so it will read a lower mass value. It does a conversion inside the scale. So it'll read a lower mass value in this case because we are accelerating downwards. Please make note, the weight of the person never changes, right? The weight of the person is dependent on their mass and the acceleration due to gravity, and neither of those things changed. Their perceived weight, or the force that they exert on the scale, has changed. That is the force that changes in this scenario. So please make sure you're aware of that. Weight is not going to change on Earth, but the normal force, which is in this case what we're dealing with here, can go up or go down to accommodate objects that are accelerating. And so please move on now to the practice problems for vertical acceleration and net force, and I will see you in the next video.